Our next speaker is Tao. He's going to talk about helical magnetic fields in IRAS 4A, in the IRAS 4A protostellar molecular outflow.
This is good. Hi everyone, my name is Tao-Chung Ching. I'm a PhD student from Taiwan University, Taiwan. So today I will talk about the magnetic field structure in protostellar outflows. My supervisor is Shiping Lai, and the collaborator include Jose Miquel and Ron. They are sitting here. So why we want to know the magnetic field in the protostellar outflow? Because protostellar outflow is the most significant and obvious feature of star formation in low mass star. So even in the very earlier stage of star formation at class 0, that the protostar is hid in behind the opaque dust envelope, and you cannot find the disk because they are probably too small by current resolution. But you still can see the very prominent and elongated outflow with thousands, even 10,000 AU scale. So it is interesting to know how this outflow launched and how do they collimate it at this large scale. So in theory, people believe that magnetic field plays a significant role in launch and alignment this outflow. So in the disk plane, you will have this poloidal or hourglass structure. Once this hourglass structure reach a critical angle of 60 degrees with respect to the disk plane, the material on the disk will launch along the magnetic field line, and the toroidal field, the Hooke stress of the toroidal field will align this flying material into a collimated outflow. So depending on the launch place of this wing, they could be a slow velocity outflow with wide opening angle, or high velocity jet with a small opening angle. So in total, people expect that the magnetic field in the jet, in the outflow, should be a helical structure like the white ones here. So because molecular outflow has very weak emission in dust polarization, so the only method to probe magnetic field in molecular outflow is through the Girart effect. So basically, it's just like the Zeeman effect in molecular line. So if the molecular line is on the plane of sky, the Zeeman effect predicts that you will have linear polarization, either parallel or perpendicular to the magnetic field line. So in order to solve this ambiguity about the orientation between molecular line polarization and magnetic field, we can get the help of dust polarization or theoretical modeling, which I will talk about later. That how do I answer the molecular line polarization with respect to magnetic field line later. So the first object has been mapped with Girart effect is NGC 3033 IRAS4A in CO 2:1 with BIMA. So here with SMA, we observe this source again. So this source probably is the most well-known class 0 source. The hourglass magnetic field from dust polarization show a textbook example of magnetic dominant star formation region, and it also launched very prominent and collimated outflow. Here is the CO outflow from VOA. So this source is a binary object, 4A and 4AY and 4A2. So these two sources are just these two dots here. So with SMA, this is our main result of CO 322 polarization maps. There are many information included here. So this contour shows the total Stokes I emission of this outflow, which will tell us the structure of outflow. And here, the vectors shows the polarization detection in E field direction. So I will talk about how do we identify the magnetic field structure from this polarization map, and also more importantly, what's the role of magnetic field played in this outflow. So first talk about the outflow structure. So this is the channel map of the CO 322 outflow at high resolution, and this is a PV diagram. So you can see there's a shell, opening shell, with different radii at different velocity. So basically, it tells you that there's a expanding shell structure and also the parabolic emission in PV diagram. So I use empirical model to simulate this CO emission and find that this channel map can be explained by two pairs of CO outflow, one from 4A1 along this direction, and the other is from 4A2 along this direction. And beside this outflow, this object also includes high velocity jet, which is this elongated part and this high velocity component in the PV diagram. So for 4A2, this object launched low velocity outflow and high velocity jet at the same time. And more interesting, if you look the jet from 4A1, it's bent to the direction of 4A2 here. So how is it bent? While the jet is bent to different direction. So if we compare with the SIL outflow, the outflow I identified for 4A2 is the very elongated large SIL outflow here, and here the small component from 4A1 is the component here. So for CO polarization, remember that the CO polarization could be either parallel or perpendicular to magnetic field. So in order to solve this ambiguity, first I compare with dust polarization. So here this is a zoom map of CO polarization in red and blue compared to the magnetic field derived from dust polarization, which is the black vectors here. So you can tell that the red vectors are perfectly matched with the magnetic field at the center of the source and start to have small deviate at larger distance from this dust core. So from this we can tell that the magnetic field inferred from CO polarization is parallel to the magnetic field inferred from dust polarization. And the other way is we also run the Girart class fast model to predict the CO polarization emission. And it turned out that the magnetic field parallel to the polarization will give you larger polarization percentage, which is consistent with our detection. And if the magnetic field is perpendicular to the polarization, then the polarization will just below 1%, which is lower than our SMA sensitivity. So the CO polarization here should be parallel to magnetic field. Also, from the velocity of the polarized emission, we can tell that the magnetic field here is belong to the magnetic field of the low velocity outflow. It is not belong to the high velocity jet that we see here. So overall, if you connect the polarization vector here, polarization parallel to magnetic field, so we can tell that the magnetic field in this blue shift load show a helical structure wrapping this outflow. But in the blue shift part, the polarization emission is more complex. Some vertical vector here and the horizontal vector here. So right now we don't have a good story for the magnetic field in the blue shift loop here. So what's the magnetic field that show from the outflow? If we compare this magnetic field structure with the dust polarization of the envelope, the field direction is very different to this cloud or to this hourglass source. And here, compared to the CO 2:1 polarization, we have one vector here perfectly matched between CO 2:1 in green, polarization in green vector, and our CO 3:2 polarization in red. So here it shows that the magnetic field we revealed here are truly the magnetic field of the outflow. It is not of the envelope, it is not of the jet. So what's the role of magnetic field played in this outflow? So there's an independent work of PDBI people. They also find two jets from these two sources, and the jets they identified are band with S shape here and a little bit C shape here. So what's the mechanism to bend this outflow? And also, sorry, in our result that this is bending in 4A1 jet. So it is possible that the bending for this outflow is due to the Lorentz force for the current of one outflow and act with the magnetic field of the other jet. So if the magnetic field is about 10 to 100 microgauss in outflow, then the Lorentz force can bend this outflow to about 10 degrees, just like what we found in our map. And also in the simulation of Murphy et al., they put a vertical magnetic field in the Z direction here, and they show that the interaction between two outflow due to the magnetic field can be merged into one main outflow. So we think that this is representative to the story here. We have two outflow launched from two jets, and due to the helical magnetic field, the outflow in the redshift is merged into one. So also here the hourglass does polarization in the envelope, and the magnetic field in the outflow seems to be a perfect story of magnetized star formation. But is that true? If we compare the rotation of this source, here the rotation of 4A to this core have different direction to the direction of our C17O data. So here seems that maybe other mechanism other than magnetic field also plays significant role in fragment of this binary source. And one more thing that we also study the Stokes V emission from this source, and I think this is the first paper of SMA talk about the Stokes V detection, and we found that the Stokes V is scaled to the Stokes I, probably due to that SMA is not ideal for Stokes V emission. However, Stokes V is more weak compared to Stokes Q, so Stokes V basically will not change our finding of helical magnetic field here. Thank you.
Questions, please? Paulo?
So for the blue shifted emission that you have, I noticed that you see the usual, I mean, what we've seen of the Gauss-Laffitte effect, the 90-degree ambiguity. Have you considered doing the radiative transfer modeling to untangle that?
No. So for the modeling right now, we can expand in the redshift power, but for the blue shift power, we don't have a good answer for the polarization detection here.
Because one of the things that we did, and we did that with Chiping, Chiping did the CO221, I did the CO120, and we found that one was perpendicular to the other on the R21OH. So in order to solve that, we modeled the whole radiative transfer problem and saw that the actual polarization, depending on the emission that you are tracing, is really sensitive to the sources of anisotropy that the actual gas is facing. So in principle, if you do modeling, you may be able to disentangle the ambiguity and have an idea what the true morphology of the field is.
Yeah. So well, for the blue shift power, we have one BMAR detection, CO 2-to-1 here. So in order to achieve those modeling, comparing different polarization from different transition, we probably will need a better detection in CO 2-to-1 in the future.
Okay, thank you. Let's move to the next talk. Let's thank again Tao.